Derivatives of trigonometric functions, section 3.3. What we have in this section is the limit as x goes to 0 of sine of x over x is 1, and we will prove this later on. And also the limit as x goes to 0 of 1 minus cosine x over x is the same as the limit as x goes to 0 of cosine x minus 1 over x, and this equals 1. 0. In either case is 0. So we are interested to learn how to find the derivatives of trigonometric functions. We start with y equals sine of x. What would be the derivative for this function? Y prime, I can tell you it's cosine x. And why is that? Let's prove where that came from. So we assume the function of x is sine x. The main definition of the derivative is that f prime of x equals limit as h goes to 0 of sine. It's f of x plus h, so it's sine x plus h minus sine of x all over h. But if we pass the limit, this is going to give us 0 over 0. So what do we do here? We rewrite the top as sine x sine cosine h plus cosine x sine h by the formula, minus keep sine x the same all over h. And now to work this out in a tricky way or smart way, we group these two together by factoring sine x out. That will give cosine h minus 1 plus cosine x sine h all over h. The limit as h goes to 0, we take this cosine h minus 1 all over h plus limit as h goes to 0, cosine x sine h all over h. Since sine x is independent of h goes to 0, the limit, you can take the sine x out, limit as h goes to 0, cosine h minus 1 over h. Same thing, cosine x out, limit as h goes to 0 of sine h all over h. This one we stated earlier, this is 0, and cosine h over h is 1. So that's why it gives us cosine x. So the derivative of sine is cosine. And to apply something like this, we look at an example, y equals x cubed times sine x, to apply it. And since you heard about the word times, means that reminds us about the product rule. So the first step is use the product rule, which says you find the derivative of the first one times the second one plus the first one times the derivative of the second one. So then from here to here by the product rule, the derivative of x cubed is 3x squared, keep the sine x the same, plus x cubed the same, derivative of sine is cosine, and that's it. Other examples, say 1 minus sine x all over x squared. So when we say all over or divided by, this means we can use quotient rule. So y prime would be the bottom one times the derivative of the top minus the derivative of the bottom times the top all over the denominator square. So y prime equals, you can factor an x out, so they'll leave an x times 0 minus cosine x minus 2 times 1 minus sine x all over x to the fourth. Then y prime equals, you can reduce the x's, negative x cosine x minus 2 plus 2 sine x all over x to the third, because we reduced the x from the top here by x1 x cubed. So this is for sine. Is there a derivative for cosine and other trigonometric functions? The answer is yes. So again, if y equals sine x, y prime is cosine x, and we proved y. If y equals cosine x, y prime is negative sine x, and we can prove it the same way as we proved the first one. How about tangent? Tangent of x, y prime is secant square of x. How about cotangent? Y prime would be negative cosecant square of x. How about secant? Secant of x. Y prime is going to be secant tangent. And for cosecant, what's y prime is negative cosecant cotangent. To apply these formulas, we need to find y prime for each of the following. Let's take an example. Y equals 2x cubed minus 3 cosine of x plus secant of x plus 20. This is an example. And we're going to look at another example. Y equals sine of t over 1 minus tangent t. So to find the derivative for the first one, y prime, the derivative of 2x cubed is 6x squared minus 3. Derivative of cosine is negative sine of x, and derivative of secant is secant tan plus 0. This simplifies to 6x squared plus 3 sine of x plus secant of x tan x. What about the next one? Y prime. We take the denominator times the derivative of sine of x, which is sine of t cosine t, minus the derivative of this, which is 0, minus derivative of tangent is secant square of t, times the numerator, and we keep the denominator the same and get it squared. Now we need to simplify the numerator. Multiply 1 times cosine t is cosine t, minus tangent times cosine. Tangent is sine over cosine, so the cosines will cancel. That will leave only sine of t, plus secant square t sine of t all over 1 minus tangent of t all squared. And nothing can else be done for this. So the more examples you do, the better for you. The best way to memorize all of them with practice. Now we go back and try to apply more of the first thing that we started with, how we find limits using the two. Those are actually theorems, that the limit of sine x over x. Let me write them again. Limit of sine x over x as x approaches 0 is 1, and the limit of cosine x minus 1 over x as x approaches 0 is 0. These are two theorems. So how do we apply them here for this one? Well, that theorem on the right side works based on the fact that these two will match. X, 2x, 2x, 3x, 3x. So here I have only 8x. I don't have the 8. So the first step we need to do is to multiply the denominator by 8. And if we do 8 here, we have to multiply the top by 8. And this 8 can be taken outside. Limit of sine 8x over 8x as x approaches 0. This would give us 8 times this one. Now it's 1 based on that theorem, and the answer would be 8. The answer would be 8. We may look at another example. Find the limit as x goes to 0 of sine of x squared over x. To do so, we need to multiply the denominator by x to make it match, and the same thing on the top. But this x cannot be taken out, so we do the limit as x goes to 0 for this x times the limit of sine of x squared over x squared as x approaches 0. So this is 0 times the limit of this is 1, and that would give us 0. The next one, the limit as theta goes to 0 of cosine of theta minus 1 over 2 theta squared. This one is slightly tricky, more tricky than the other ones. If you pass the limit, that will give us 0 over 0. And if we rewrite it as cosine theta minus 1 over theta times 1 over 2 theta, we can't get an answer for that. So one trick to do here is to rationalize the numerator by multiplying by the conjugate. So keep this the same. Multiply by cosine theta plus 1, top and bottom. And what do we get for the top one? It's cosine squared theta minus 1 over 2 theta squared times cosine theta plus 1. We can factor a negative on the top, and we can take the 2 out, so I factor a negative 1. The top becomes 1 minus cosine squared theta over theta squared times cosine theta plus 1. But what is 1 minus cosine squared? That's sine squared. So it's negative 1/2 limit of sine squared theta over theta squared times cosine theta plus 1 as theta goes to 0. This equals negative 1/2 times, I'm going to split this into sine squared theta over theta squared, and the limit of 1 over, that's because that's sine squared theta times 1, cosine theta plus 1 as theta approaches 0. Theta approaches 0. And what we can do with the sine square, we can rewrite it as sine theta over theta all square as theta approaches 0. And the other one stays the same. The next thing is we may pass the limit inside, limit as theta goes to 0 of sine theta over theta all square times the limit as theta goes to 0 of 1 over cosine theta plus 1. So this gives us negative 1/2. Inside this we know it's 1 square times 1 over cosine 0 is 1 plus 1, and that would give us negative 1/2 times 1 times 1/2. So the answer is negative 1/4. Again, there's only 2 theorems. We always need to rewrite the given expression in a way that either one or probably both at the same time can be used to calculate the limit. And again, as I said, later on we'll see how to prove them, where they came from. But that's how we apply them. That's how we apply them.